Today we are very happy to have Katherine Deck visiting from Caltech. She's been doing work on exoplanet and nonlinear dynamics, and she's going to tell us about all this.
Okay, so thank you. It's great to be back here. So again, I'd like to start by acknowledging my collaborators. The work I'm describing today has been done with Eric Egel, Matt Holman, and also Matt Payne. And so broadly today I'm going to be talking about exoplanet formation and evolution. But what you'll see as I go through this talk is that really to understand this, it's key for us to understand the orbital dynamics of systems pretty much at every time scale in which those interactions occur. To begin with, most of the research, or a lot of research on exoplanets is motivated by the desire to understand our own solar system better. The solar system has a number of sort of macroscopic features. So these are things like the fact that there are giant planets and ice giants that are found far out in our system, and there's terrestrial planets that are close in, and nothing interior to the orbit of Mercury. The orbits of the solar system planets also reveal something about how they formed and evolved. For the solar system, the orbits are what we call dynamically cold. The orbital planes of all the planets coincide, roughly. So they're nearly coplanar, and that orbital plane is also lined up with the equator of our sun. Furthermore, the eccentricities of these orbits are all low, with the exception of Mercury. And so these features of the solar system are key observables that theories of formation and evolution of the solar system need to match. The issue is, though, that 20 years ago, the solar system was our only known example of a planetary system, and so it was impossible to test these theories of planet formation and evolution because we weren't sure if the solar system was somehow just some special realization or some special outcome of that process, or if it'd be general to the systems that we'd see outside the solar system as well. And so now that we've discovered thousands of exoplanets, we can begin to put the solar system into a bigger context and try and understand how common solar systems or planetary systems like our own actually are. So to begin with, exoplanet observations have revealed that planetary systems can be incredibly diverse. We know that systems can be found very, very far from their host star. This is the HR8799 image. It's a directly imaged system. So what you're seeing here, this is actually the black body emission from the planets. These are very young planets, so they're still hot, and that's why we can see them. And you can only see them after you block out light from the central star. So these planets, they're all very massive. There's several Jupiter masses, and the scale of the system is also very large, many tens of AU, in comparison to our own solar system where things take place much closer to the star. On the other hand, we know that systems can also be found much, much closer to their star than the solar system.
Yes. You said, going back to the last figure, those weren't actually, you just put on the image of the planets, right?
No, that's actually the image.
That's from a telescope.
Yeah. The date is 2008. I thought that it was only now that people could do that.
No, so this was I think this was the press release image for this system.
This is the poster child, because they're very young, so the planets are very hot.
I see.
It's
Okay.
actually thermal.
She said that, yeah.
I'm sorry.
So we also know, though, that at the other extreme, systems can be found very near to their host stars. And one particularly striking example of that is the KOI 500 system. So if you can read this, it has this system has 5 planets. They all have orbital periods less than 10 days, and they're all bigger than the Earth. And if you add up roughly what the mass in the planets for this system is, you find that you have something like 20 Earth masses of material in planets within 1/10 of an AU, and in contrast, the solar system has 1/10 of that mass in a distance 10 times that big. So something about this system appears very strikingly different than the solar system. Similarly, we know that planetary orbits can be misaligned. It's not true that planets' orbits always need to be aligned with the host star's spin. Kepler 56, this is an example of that, where you have 2 planets that share a common orbital plane, but that orbital plane is misaligned with respect to the star. And this misalignment is thought to be due to the dynamical influence of a distant body. Furthermore, we know that this rule of circular orbits in the solar system is definitely not a rule at all. And that's particularly striking for the giant planet population. So here I'm plotting the orbital eccentricity. These are for planets that are bigger than 1/5 the mass of Jupiter. As a function of their orbital period. The different colors just denote whether or not these planets were found in single planet systems or whether we know that there's other planets present in those systems. And what you can see is that the eccentricities are basically they're very broad, and you can find planets with almost any eccentricity at all.
And are those eccentricities all well measured, or are some of those low ones consistent with 0? Do you know?
I'm sure some of the low ones are consistent with 0, yeah. But definitely the high ones are well measured, I think. So another way to see this diversity of systems is on a panel of planet mass and orbital separation. And you can see that all these black points are detections. So we basically have found planets at this huge range in planet masses. This is orders of magnitude, and also in terms of their astronomical separation from their host star. So you can also see that there's sort of distinct groups of planets here. Although this diagram has a lot of observational biases, we can still pick out some definite populations. There are massive planets at large orbital distances, like HR 8799, that directly image system I mentioned before. We can identify a group of planets that are something like Jupiter analogs. So these are massive planets at large orbital distances. And we know, taking into account observational biases, that something like 11% of stars have a Jupiter-like planet with the semi-major axis less than 5 There's also this population of gas giants at very short orbital distances. These are what are called hot Jupiters. And these are comparatively much more rare. They're only found around something like 1% of Sun-like stars.
So this kind of suggestion of this plot that there might be kind of a hole between the hot Jupiters and the normal Jupiters?
Oh, up here, yeah.
Up here, is that real, or is this just a selection effect?
So that is real. It's true that it's harder to see these compared to these because the signal, the radial velocity signal goes down with orbital period, and you also need a longer baseline to characterize it. But the fact then that we see all these out here means that we should be complete there. Yeah.
So in other words, the bias is some kind of roughly monotonic, smooth thing?
Yeah, so basically it's harder to see things in general always at large orbital distances and also smaller things. So that's why there's nothing in this area down here. Yeah. But it's this smooth monotonic. Yeah. So most of the planets that I've described so far, these gas giants, have been found using the radial velocity method. So basically, the idea is just that the star is moving around the very center of the star-planet system. When the star is moving towards us, its spectrum is blue-shifted, and when it's moving away from us, it's red-shifted. So you can actually then track the line-of-sight velocity of the star. So this is data, the line-of-sight velocity of 51 peg, as it evolves in time. And this is attributable, this motion is caused by the presence of a hot Jupiter. And this was actually the first planet observed around a main sequence star, 51 peg d. Finally, there's this population down here. These are small planets orbiting close to their host star. They're intermediate in size, for the most part between Earth and Neptune, although we're also plagued by sensitivity down here. There could be a lot of things that are just too small that we haven't seen yet. It's interesting that in the solar system, we don't have a planet in this size regime. So a priori, we're not really sure if these are going to be large terrestrial planets like Earth or more scaled down Neptune, still with big atmospheres. And additionally, like I mentioned earlier, the solar system doesn't have any planets in this close to the sun. Yes, and these are systems like KY 500, which I mentioned before. So most of these systems have been found not using the radial velocity technique, but instead by transit. And most of them were found by the spacecraft telescope, which monitored the brightness of over 150,000 stars nearly continuously for 4 years. And what it was looking for was the tiny dips in light that you get when a planet passes in front of the star with respect to our line of sight. So we see this temporary dimming of the star, and then it returns to its normal brightness. So Kepler was extraordinarily successful. It found nearly 5,000 planet candidates, the majority of which are real. And if you're interested in dynamics, like I am, you'd be very happy to know that something like half of those candidates are actually part of multi-planet systems that are multi-transiting systems, where all the planets, or at least the planets that we do see, are all transiting the same star. And these planets are very common. Something like half of Sun-like stars have a small planet with a period less than 85 days, and this rate is even higher for stars that are less massive than the Sun. So taken together, what I've just shown you is that exoplanets are extremely common. Most stars do have a planet, and they're also very, very diverse. And that's what the observations have revealed to date. What's important to realize, though, is that these observations, what we're really looking at is just a fossil record of everything that came before. So, for example, there's the actual formation of the planets and their interaction with disks. So this is actually an image of a disk in the thermal emission from the dust of that disk. So this is where planets are forming and evolving. This is typically on timescales of millions of years to tens of millions of years, so the disk lifetime. So what we're seeing is the byproduct of that, and also everything that shaped the planets after they formed, on much longer timescales comparable to the age of the system. And if we want to understand this diversity, we really need to understand everything that came before. And so what I'm interested in is trying to see how much of this diversity can actually be sort of unified by understanding the physical processes that have led to it, because presumably the same physical processes act in most systems. So today I'm going to start not by actually talking about understanding those physical processes. Instead, I'm going to start by talking about work that I've done trying to characterize planets. In particular, characterize planets using their short timescale orbital interactions. And this is important because if we want to understand how planets form and evolve, if we want to make theories of them, we need to first have a well-characterized observed sample so that we can test our theories. So that's the first part. In the second part, I'll be talking about orbital dynamics on very long timescales. So my work that I've done on orbital instability of planetary systems, which can take something that appears dynamically cold, so what look like regular orbits, and over time produce systems that look very different, say with a different number of planets or very different orbital parameters. And then finally, I'll just end by looking ahead and I'm telling you a bit about some stuff that I'm excited about that's coming down the line soon. But we'll start with characterization. So the issue, or the sort of challenge for characterization for the small planets that we've seen that are the ones that are incredibly common in our galaxy is this. They were found using Kepler, so they were found in transit. So what we learned from that is the size of the planet, because a bigger planet would produce a bigger dip. And we also learned the orbital period and the phase of the orbit, because that's essentially the timescale in which that signal repeats itself. Ideally, what we want to know, though, is also the planet's masses, so we can know their densities, and then learn something about their compositions, and also their orbital parameters, so things like eccentricity, mutual inclination, and so on.
You didn't put numbers because there are big ranges for both, but
for what?
For time versus the flux.
Oh, I didn't put numbers just to make it more of a schematic, but so a Jupiter-sized planet around a sun-like star produces a 1% dip, and an Earth-sized planet produces something like a 0.1% dip. And the time scale for these transits are something like a few hours for a lot of systems. Yeah. Right.
What's the longest period that Kepler can reasonably see? Is it really limited by how long Kepler's?
Yeah, so it's primarily limited by the baseline and just the requirement that you want to see is, say, at least 2 transits. People have tried to say stuff about the single transit events based on the duration, and then they assume it's a circular orbit, and then you can maybe back out something about the period. But that's also degenerate with the transit chord on the face of the star, because that also changes the length of the transit. So I think, so if Kepler's baseline was something like 4 years, then the longest period planets are about 2 years.
And it's over.
Yeah, so the Kepler really relied on very fine pointing, and so it needed 3 reaction wheels to point very finely to be able to turn in all the different directions. And it had an extra one. Then one of them broke, and then it was using the extra one, and then that one broke. So the primary Kepler mission's over, but the actual telescope is being used still for some exoplanet science in something called K2. Okay, so the way we'd like to follow up the Kepler planets and to learn these other properties and to really well characterize them is to use radial velocity, because that tells us the planet mass and it also tells us about the orbits. The challenge is that the Kepler stars are very faint, so you need to integrate for a long time to get high enough signal to noise to measure planets. And also the signals that we're looking for of small planets on tens of day orbits, that's actually extremely challenging. That's way beyond the limits of current radial velocity techniques for the most part. And so with an incredible amount of time on one of the world's best telescopes, basically what Jeff Marcy and his group were able to come up with was something like 50 mass constraints for small planets. But as I've just told you, we know thousands of candidates that we want to learn about. So this is troubling because that means that many of the systems we care about, we can't actually characterize. Furthermore, when the actual signal that you're trying to find is so small, the actual just measurement of mass is so small, measuring a small eccentricity on top of that is essentially impossible, and you can't also then, by the same proxy, learn about small planets that aren't transiting. They're also very hard to measure. So this is an issue, and the way we're going to solve it is to take inspiration from our own solar system with the discovery of Neptune. So what Adams and Leverrier noticed was that the position of Uranus on the sky deviated from what you would expect for a Keplerian orbit. And those deviations were caused, they inferred, by the perturbations from an additional planet exterior to Uranus. I guess it was the night that Leverrier sent his prediction for where Neptune should be to Gall. Gall went to the telescope and observed it. So it's sort of this fantastic confirmation of classical mechanics. So the idea that we can take away from this, though, is to try and characterize planets by using the effect that they have on each other, whereas the detection methods rely on the effect that a planet has on the star. And so the basic idea is what's something called transit time variations, and as I mentioned, we use planet-planet interactions to learn about them. So for a transiting planet, the main observable is the transit time. That's the thing that we best measure. If you just have a single planet in the system, then that transit time, basically they always come exactly periodically because the motion is Keplerian. But when you have another planet in the system, then the motion is no longer Keplerian, so you end up with deviations. And what you'll end up with is something that looks like this. So here, this is an individual transit. The black points are data and the red is a model. And these are subsequent transits in time moving down the y-axis. These all have been lined up so that if the orbit was periodic, all the transits mid-centers would lie at this blue line. But what you can see is that each transit is shifted with respect to that. And that's because this planet is being perturbed, in this case, by a non-transiting planet. And David Nazorny and his collaborators were able to uniquely back out the mass and orbit of this non-transiting planet just by its gravitational effect on a transiting planet. So there's that promise that you can detect and characterize non-transiting planets. But even if you just have two planets that are transiting and they also have this effect, then you can learn about their masses and orbits and characterize them as well. And furthermore, if they're transiting, you know their radii, so when you learn their masses, you therefore learn their densities.
So this analysis clearly excludes two nearby planets, sandwiching the one in between,
So typically, you can say that the transit timing variations of the middle planet are just a linear combination of the two perturbations for the one on the inside and the one on the outer. So, yeah.
But is there which fit is best, or you cannot distinguish between?
So when both planets are transiting, you know where they are. And for this non-transiting case, that is the challenge. That's actually the hardest part, is trying to find the period of the non-transiting planet. And there's usually a lot of degeneracy.
When you say uniquely, so you use the word uniquely
Yes,
here.
yeah.
I mean, presumably there's some combinatoric set of possibilities in this case.
So for this case, no. Because as I'll show in a second.
Like beat frequency or something?
Yeah, so the transit timing variations are made up of essentially different harmonics. And so if you just measure one harmonic, you end up with these degeneracies. But if you measure multiple harmonics, you end up with multiple constraints on the same parameters. Yeah. Okay, so just to highlight the promise of this method, as ridiculous as it is to have a favorite system, Kepler-36 would be my favorite planetary system. It has two transiting planets. Their orbital periods are 14 and 16 days. So they're interacting very strongly with each other. And so if you lived on a version of Seattle, on the inner planet in that system, at closest approach, Kepler-36c would appear this large in the sky. And just for comparison, here is Seattle on our planet, and this is how big the moon appears in the sky. And actually, at closest approach, the distance between these two planets is only 5 times the distance between the Earth and the moon. And these planets they have a combined mass that's something like 10 times more than the Earth-Moon system. So these planets are interacting very, very strongly. And those strong interactions have actually allowed us to characterize the system in exquisite detail. This is the best characterized set of planets that we know of outside the solar system. And all of that information is coming from transit timing variations. So here are the transit timing variations for the system. This is for the inner planet and for the outer planet. I'm going to be showing you a sequence of plots that look like this. So on this y-axis, what I'm plotting is a deviation from a constant period orbit. So essentially, you take the transit times and you just subtract out the best fit line. And so you can see that here these deviations are very large. They're several hours for each planet. They're very easy for us to measure. And they're also very rich looking. It looks like there's a lot of structure here, and that's what allows us to characterize the system so well.
What is on horizontal axis?
So this is just time. Sorry, BJD. That's an astronomer's convention. It's a time axis. So these different points, in days, and so these different points are just the different subsequent transits.
What's going on with the error bars?
Yeah, so the inner planet's smaller, and so we just measure its transit time less well. And so the error bars are very large here because the data sampling rate was once every 30 minutes. And then at this point, it's switched to short cadence data. So then it was basically a data point every minute.
So the assessing on the left half goes from huge error bars to small.
Yeah, so that's the switch in cadence between a data basically measuring the brightness of the star every 30 minutes to measuring the brightness of the star every minute. So you just get much, much better sampling in the transit, which is maybe a few hours long, and that allows you to better constrain the time. So Kepler-36 is the promise of transit time variations, but out of something like 260 planets that show significant timing variations, only 60, on the order of 60, have had their times analyzed in a meaningful way. And the reason for this is primarily because the TTV inversion method is very computationally expensive. And so while RV follow-up is sort of telescopically expensive or even impossible, this TTV method is expensive in a different way. The reason for that is because every time you want to evaluate your model, which is a set of initial conditions, or basically orbital parameters for the planets and their masses, you need to integrate using your n-body integrator. And that just takes a lot of time, especially when you need to evaluate your model millions to hundreds of millions of times to converge on an answer and accurately measure the uncertainties in the parameters. So that's a challenge. Another challenge with the TTV method is that when you do it this way, the n-body integration is basically like a black box. At the end of the day, you're going to come up with a mass measurement, maybe an eccentricity measurement, but there's no understanding of what aspect in the data is actually giving you that estimate. So it's harder to, you just don't have a clearer picture of what's actually going on in your fit. And what I said, this obscuration of the physical model is especially pertinent because we know that there are degeneracies between parameters, yet we're still measuring masses. And this is particularly true near orbital period resonances. So I'm going to start by explaining this. So if you have a planetary system that's near a mean motion resonance or an orbital period resonance, that's when the orbital period between the two planets forms a rational number. So suppose now we have a configuration where the outer planet has twice the period of the inner planet. And we're starting them at this longitude of conjunctions. This is where the planets are interacting most strongly. So as the planets interact, or as they evolve and then they interact, what you see is that where they interact always stays at the same place in the orbits. So what this means is that even though each conjunction, each time the planets meet each other, their individual interactions are extremely small, they can add coherently and produce a larger effect. So resonances are actually where transit time variations are most observable because these gravitational impulses add coherently there. More generally, if you have a system that's not exactly at the right period ratio, but just slightly offset from it by an amount epsilon, then what happens is where the planets meet each other and where they're interacting circulates slowly about the orbit, but still you have this coherent addition of small perturbations, and that gives you an observable effect. So what a number of people have shown by studying these resonances analytically is that the structure of transit time variations near resonance should be sinusoidal, and the timescale for that sinusoidal is basically the timescale for that where the planets meet each other to circulate about the orbit, as I just showed you in that video. And also, these transit time variations are anti-correlated. So here, this is real data for the Planet Hunters 3 system. It's near the 2-to-1 resonance for the inner planet and for the outer planet. Again, these are the TTVs. These are now in minutes as a function of time, in days. The tricky thing here is that what the analytic work shows is that the amplitude and you get one phase from these because you have the anti-correlated constraint. The amplitudes of the two planets and their phases depend on both the mass and eccentricities of the two planets. But you only have 3 observables because you only have 2 amplitudes in one phase. And so that's fundamentally just not enough to measure everything you care about. So that's this mass eccentricity degeneracy. The solution to it is to realize that the TTVs are not just that one sinusoidal component. So here I'm showing again, this is for Planet Hunters 3. The black is the data. And the blue now is the set of numerical solutions to this data through a numerical fit to the data. And what you can see is that there's these short period interactions on top of this resonant TTV signal. And that's actually due to this individual conjunctions. The resonant signal is the coherent addition of small perturbations over that circulation timescale, and these individual bumps are just due to one conjunction to the next. So they're much smaller to measure, but if you can measure them, as I'll show, they're incredibly important. Because
what is TTV?
Oh, sorry, TTV is this transit timing variation. So that's the offset from a perfectly periodic orbit. So if a planet was on a Keplerian orbit, this would just be 0. You would see no TTVs.
Okay, you also said that when they're on a line, you understand that there's an interaction.
Mm-hmm.
But what is the effect of that? What does that do?
Oh, so it's just that's just when the planets are close to each other. So
Right.
the gravitational interaction between them, yeah.
Well, but why does it matter? You know, so if there's a rational number, then of course it happens the same place relative to the sun. But why does it matter? I mean, that no matter what the ratios are, the small, you know, the faster orbit and the slower, they'll pass each other.
Yeah.
Line. Why does it matter? You know, that it's in the same place or not? I didn't understand.
Yeah. So the reason why it matters is that if those interactions happened at random places throughout the orbit,
Right.
then they would just sort of average out. The next one would not be correlated at all with the one that happened before it. Whereas if they happen at the same place in the orbits, the same phase of the orbits, then the planets are always meeting each other in the same way and leaving each other in the same way. So each interaction is correlated with the one before it. It's similar to the one before it. So it can add over time to produce this larger effect.
And what is the exact effect?
Oh, the effect is these transit time variations.
The transit time variation.
Yeah. Yeah.
You think of it as just the mutual gravitational interaction of the two planets.
Yeah,
So
that's
then
all.
Simply, once their orbits to deflect a little, is that what?
Yeah, that's all. Yeah, all of this is just gravitational interaction between planets. But just to understand what these different timescales are, it's helpful to think about the conjunctions between planets when they meet each other, and that's what tells you whether or not you get this large amplitude, slowly varying piece when they're near this resonance, or whether or not you get these shorter amplitude.
I guess my confusion is that I can see the effect if they have elliptical orbits. They had circular orbits. I guess I don't see why there's any effect.
So even if you start with circular orbits, you'll induce eccentricity. So there's no such thing as circular orbits.
No, I agree. If there's
in some
eccentricity, I see that
Yeah.
you don't get an effect.
Yeah.
What I'm saying is that if you actually had perfect circular orbits, then I don't see.
Well, yeah, but also you can't maintain perfectly circular orbits.
Agreed.
Yeah.
I'm just trying to understand
Yeah.
what the actual physics of the effect is. I think I get it. So,
Okay. No. That's
Go
But I
on.
think this is a sign of essentially the induced eccentricity.
Yeah. So that's part of when I said that the amplitude depends on the eccentricity, partially because of that.
I'm not sure I even understand Dan's point. If it's perfectly circular, why can't there be any effect?
No, what I'm saying is I didn't say that.
Suppose it, right, and then it evolves, but
No,
are you
what
saying
I'm
it
saying is
can't
that
evolve from?
No, I'm not saying anything like that. All I'm saying is that if an orbit is perfectly circular, then all that matters is that the two pass each other and that you have an effect aligned with the sun. But where that happens in a circular orbit, all points are equivalent, so it shouldn't matter.
No, because it's not a fixed angular velocity, right?
It's not, when you have, right. Are you talking about an elliptical orbit? No.
So you are right that when they have perfectly circular orbits, then this resonant effect can't happen.
Yes.
And that's absolutely true.
Okay. Yeah, no, I
But they can still interact with each other.
Right,
Yeah,
of course.
yeah,
No, I agree
yeah.
with that. Okay.
Okay.
Sorry for
No, that's okay.
Go on.
Is this consideration for two planets whose orbital planes are the same or more or less the same, or it can be perpendicular too?
So the analysis that we're thinking about here is when the planes are nearly aligned, because that most closely corresponds to the real systems where you see the planets both transit. But if they're misaligned, then you would have to change the analysis. Yeah. Because then they most often interact when the orbital planes cross. So the point though is that although there's this degeneracy between mass and eccentricity in this resonant component, the short period components, as I'll show you, they depend on the orbital parameters in a different way. And so they can be used to break this degeneracy between mass and eccentricity. And in fact, they even give you the masses uniquely with no dependence on eccentricity. So as I've said, TTVs are a deviation from a constant period Keplerian orbit. And so we can use that to actually, I'm just going to sketch how we derive them. The basic setup is that you have two planets. They're essentially on nearly circular orbits with semi-major axes A1 and A2. And this lambda, this is the angle specifying where the planet is in its orbit. Psi here is what's called the synodic angle. It's just the angle between the two planets. So when this angle is 0, that's when the planets are at conjunction and interacting with each other very strongly. So we pursue this derivation in the Hamiltonian framework. And in that context, you need canonical variables. And so I'm not going to actually explicitly say what they are, but I'll just say this angle lambda, the small angle lambda, is canonical, and it's conjugate to a momentum that depends on the semi-major axis of the planets. So we can write the Hamiltonian in this way. It's composed of a Keplerian part, which depends only on momenta, and an interaction piece that depends on the momenta and the angles of each planet. This interaction at 0th order in eccentricity only depends on the angle between the two planets. And the fact that it only depends on the angle between the two planets is a sign that there's no preferred direction. There's no preferred reference direction. So what we seek is a canonical transformation such that in the new variables, when you write the Hamiltonian in the new variables, it looks like a Keplerian Hamiltonian plus higher order correction terms. Because then for this system, the equations of motion say that the semi-major axis is constant and the angle of the planet just advances linearly in time. So the transformation between the real system and this average system is precisely then the transformation that gives you transit time variations, because those variations are the difference between a real system with interacting planets and an average one, which corresponds to a Keplerian orbit. So from this canonical transformation, then we can drive the transit time variations, and they take this form. So the transit time variations of the inner planet, they depend linearly on its own period, because its own period, it sort of sets the scale for the system. So if you have longer period orbits, then the same perturbation, it's basically the same fractional perturbation, and then you end up with larger transit time variation. If you have a larger perturbing planet relative to the mass of the star, so this M2 is the mass of the perturbing planet, you also get larger transit time variations. Both of these are written as a sum over harmonics of the synodic angle, which again, this is the angle that's telling you where conjunctions happen. And finally, there's this amplitude coefficient, which depends only on the semi-major axes of the two planets, and in particular, only on their ratio. So for very widely spaced systems, the planets have very different angular velocities, and so when they pass each other, it's very quick. And so you only need the first term in the sum that just says there's an interaction once every time the planets meet, and just when they meet. But as you push the planets closer and closer together, then each individual interaction takes longer, because their relative orbital speeds are slower, and so you need more terms in the sum to accurately represent the TTV signal then. What's exciting is that if two planets transit, you know both of their orbital periods, and so you know these two parameters, and you also know the semi-major axis ratio, because you learned that from the period ratio. You also know the phase of the planets in their transit, and so that determines how this angle psi evolves in time. And what that means is that if you can measure these transit time variations for any of these harmonics, the only unknown on the right-hand side is the mass of the perturbing planet. And so measuring these TTVs that are associated with conjunction to conjunction immediately tells you the masses of the perturbing planets. If you do have a system that's near resonance, you can use this to break the degeneracy between mass and eccentricity, and then also learn about the eccentricities of the planets. So here's some results just showing this and how this works for the Planet Hunters 3 system. That was the one I showed you before. This is the mass of the outer planet in that system and the mass of the inner planet. And these are the results of fits to the data using different models. So first, this is the confidence contour we get, our uncertainty levels associated with the two masses when we only fit that large amplitude sinusoid associated with the near resonance. And you can see that we don't measure the masses very well, and the reason for that is because of this degeneracy with the eccentricities of the planets. If you just fit this short period synodic TTV associated with conjunctions in the inner planet's TTVs, you learn about the mass of the outer planet because that's the planet that's perturbing it. And that gives you this very tight constraint on the mass of the outer planet. When you combine them two, you get this orange air ellipse.
What are they? This is 1 sigma?
Yeah,
Okay.
yeah. I think. I have to check. I'm pretty sure, yeah. Yeah, and so when you combine them, you get this resulting air ellipse. And in comparison, when you do a full n-body analysis, which takes into account all of the interaction terms between the two planets, you get this blue contour here. So there's two takeaways from this. The first is that this short period synodic TTV associated with conjunctions, this really is an important piece that gives you the masses of the planets because it breaks its degeneracy. And the second takeaway is that the analytic TTV formula basically has all of the information about the masses in it compared to the n-body integration. So this is very useful because this addresses that challenge that I mentioned at the very beginning, which n-body integration is like a black box. We don't know where these parameter constraints come from. But when you have an analytic formula, you immediately learn what aspect of the transit time variation is giving you your mass measurement, for example. So here are some results.
Sorry, can I ask
yeah.
about should I be worried about the fact that these contours are like the mass of the outer planet? Sort of like, there seems like there's some tension between the resonant and the short.
Yeah. Okay. So what I can say is that the resonant TTV is approximate. That formula is approximate, and in particular, I'm using a version of the formula that only works when you're very near the resonance, and it breaks down as you move away. So this system, what that's telling you is actually not that there's anything to worry about, but more that that formula, the assumptions that went into driving it aren't exactly met for this system.
Okay. And you would be able to identify that if you looked at the...
Yeah, I think that like when we looked at the parameters for the system, we kind of knew that, okay, at this period ratio, they're far enough away from resonance that there's going to be some amount of error. Yeah.
Do I understand this right, that you can't do it this way because the other planets don't like?
Yes, yeah, exactly, yeah. Okay, so here are some results. I think this is some of the most exciting stuff that's come out of transit timing variations. So here I'm showing the measurement in Earth masses of planet masses and planet radii. So this is coming from just the transits. The masses here, if they're black points, these are the 1 sigma error bars. If they're black, they're coming from radial velocity, and if they're orange, they're coming from transit timing variations. And what you can see is that the orange points are sort of systematically lower than the black points. And that's because this TTV method is able to it basically suffers from different observational biases than the radial velocity method. And so it's not as sensitive to, although more massive planets also produce a larger TTV signal, just like they do for a larger radial velocity signal, they're not as sensitive to it. And so with TTVs, we're probing these low density planets.
Sorry, is it the case that where it seems like all the orange ones, the TTV ones, are pretty closely aligned with something above? Are those just different measurements from the same?
No, so there's actually very few systems that have both a TTV mass and an RV mass, and a radial velocity mass. So these are all for different systems. But what's interesting is that some of these planets, so they're so low mass at their radius, which means they're so low density that they must have a large atmosphere. And that's interesting because that places constraints on where they might have formed. And so that's sort of one of the implications that's coming out of this work. And just for reference, this is where Kepler-36, that system with the very extreme transit time variations, would lie. This is the best measured mass for a small planet, and it came from transit timing variations. So I had said at the beginning that one of the challenges with TTVs is that it's very computationally expensive, and that's because you have to do n-body integration at every model evaluation. So it might take something like weeks to months with a standard n-body integration to measure masses and well characterize the uncertainties with a standard n-body integration. And even with an optimized n-body integration, like code that I wrote, which we call TTV fast after CMB fast, it takes days to weeks to fully analyze the problem. But with the formula, you can evaluate these systems much, much more quickly. It can take minutes to hours to days with our code that is based on the analytic formulae. And so I'm happy to see that this approach of fitting TTVs using analytic formulae is being adopted. And so soon we'll be able to add, I believe, like hundreds of planets to this system based on the work now of Haddon and Lithwick, who are using this formula.
So this week's is from running all the simulations you need to make the error band, or for one of them?
No. So that's one is not that much time, but to accurately characterize the uncertainties.
So
Yeah.
have you looked? I mean, there are these techniques where you do when you have a black box like that you can run a derivative through it using automatic differentiation,
Mm-hmm.
and so then it starts to be some sort of hybrid because you're doing basically calculus, but on a black box, right? So.
Yeah.
That seems like some possibility because then it's the same evaluation time for one as to get the derivative.
Yeah.
And you can do that bootstrap to get second derivatives. Has there been any?
I definitely talked about doing that with some of my collaborators, but no one's actually mustered up the courage to do it yet. Yeah.
So the earlier work you showed, were they using TTV fast?
So some of this is using TTV fast, and some of these are done by groups that have developed their own code. Yeah. Okay, so, and then the second challenge was that there's this black box, and it's sort of unsatisfying that you end up with these measurements. without knowing where they come from. And so what I've shown you is that these short timescale interactions between planets that are associated with every conjunction tell you about masses, and these resonant TTVs that happen on timescales of hundreds of orbital periods, those tell you about the planet eccentricities. So I'm going to switch now to the second part of my talk, which is about the long-term interactions between planetary systems. And ultimately, this is what we want to understand. The characterization is just so we can better understand or better test our theories and develop theories. So yeah, to begin with, I'm going to start again with the solar system. The question of long-term stability of planetary systems is just a special example of the gravitational n-body problem, which is this classic problem of classical mechanics. And most work on this problem historically has been in the context of the stability of the solar system. So this problem could be analyzed really rigorously, first when Newton wrote down the equations of motion and wrote down the law of gravity. Based on this law of gravity and even taking into account interactions between planets, there are proofs, or erroneous proofs, of the long-term stability of the system. So Laplace and Lagrange, for example, thought they had an argument for why the interactions between the planets would average out over long timescales, and so that the system as a whole would remain completely regular and orderly for all of time. And sort of that picture is enshrined in what's called an orrery, which shows that the planet's evolution evolves just like clockwork. So the first hint that something might be wrong with this picture probably came from Poincaré, who in his analysis of the three-body problem discovered that there are these strange orbits, which we now call chaotic orbits, that basically these orbits were strange in that even though they might correspond to regular orbits, or things that look like regular orbits, on very long timescales, you weren't sure what they were actually going to do.
I thought Newton also understood that. And he
Yeah.
thought God was coming in and correcting or something.
Yeah, so he did. There is a famous quote of his, that says that maybe it would take intervention from God to sort of correct it at every, So the idea of chaos, though, if you're not familiar with it, it's basically the idea that a chaotic trajectory will exhibit sensitive dependence on initial conditions. So a small perturbation to that trajectory will exponentially diverge. And the reason why this is important for stability is because it tells you that chaotic orbits are essentially efficient at exploring phase space. So while a regular orbit is more constrained, this chaotic trajectory can explore a bit, and if it explores enough, it might find a region of phase space that corresponds to unstable orbits, and therefore start to show instability. So for the solar system, we could actually say for sure that the orbits were chaotic only then in the 1980s when computers got fast enough. So both Jerry Sussman and Jack Wisdom and also Jacques Lascar showed this independently, that the solar system is chaotic. And so this orderly picture of an orrery was not correct. And furthermore, this chaos does have a probability of leading to instability. So in 2009, it was shown that within all the uncertainties that we know on the current positions and velocities of the planets and several larger small bodies in the solar system, there's a few percent chance that Mercury can collide with the Earth or Venus in the future. And similarly, so that occurs on timescales of many gigayears in the future. But because of the reversibility of the equations of motion in time, you can also sort of infer then that might have also happened many gigayears in the past. And indeed, an orbital instability in the past has been invoked to explain what's called the late heavy bombardment. This is within the context of the Nice theory, which is the leading theory for the evolution of the solar system, and that might explain the cratering record on the moon. So where this instability of the giant planets caused this influx of small bodies, which produces the craters. For exoplanet systems, there is evidence that instability is also important. So for gas giants, again, I showed you this eccentricity distribution, and it's thought that planet-planet scattering can account for this. Furthermore, the highest eccentricity seen, that's correlated with the host stars of those planets having a greater metal enrichment. And we know that a greater metal enrichment in the host star also corresponds to a higher likelihood of giant planets. And the idea is that you have more solid material around when the disk is there, so you form more giant planets. If there's more giant planets, then you have a greater chance for instability, and that's why there's this correlation between the two.
So also coming back to the solar system, I mean, the formation of the moon has been suggested due to the impact of a Mars-sized planet back in the very early times.
Yeah.
So that would be definitely one kind of very obvious
source of instability. So, Yeah, we also think that hot Jupiters might be explained by orbital instability, or at least some fraction of them might be, because the canonical wisdom is that these can't have formed where we see them today, because there's not enough gas around. And so the idea is that if there was some planet scattering event, one of these planets might have come in on a very high eccentricity orbit, and when it's at pericenter, the tides raised on the planet by the star can circularize it, and then it ends up on this short period orbit close to its host star.
So I guess,
No, I'm sorry. No, I'm just wondering, so is that an explanation for our Jupiter or for other Jovian-sized gas planets?
Which explanation?
The one that you just said.
Oh, that's only for things that have these very short orbital periods.
Oh, I see.
Yeah.
I see.
Yeah.
There was enough gas to form our Jupiter.
Yeah, at these larger distances,
Yeah,
yes.
okay,
Yeah.
okay.
Yeah. So, and actually in days, you can't tell just based on this, but these are orbits of 3 days or something like that.
Okay, I'm sorry, Maureen.
so whatever happened to have it, if it's not formed in situ, but if whatever scattering or migration had happened, it must have been very quick, right?
Yes.
Because otherwise you would have, as I mentioned earlier, that was my question, is like whether there's some kind of observational bias that you don't see population between the hot Jupiters and the normal Jupiters. But,
Yeah.
So do people do that, try to see that if there was some kind of orderly, of some sort of migration, I guess scattering is faster, but if there was some kind of...
You would see that whole space was filled in.
Exactly,
Yeah.
in some form.
Yeah, I think that is actually one reason, or that sort of ties into this theory too, is that you scatter things in, they have very high eccentricity, and they circularize here, and these are things that would be more intermediate that don't happen as often. So the question that remains, though, and something that I'm very interested in trying to understand, is whether or not instability is also important for small planets, because those represent actually the largest population of planets that we know about. So this is sort of a general question: is instability important for these small planets, which I'm calling Kepler systems because most of them were found by Kepler. And so to sharpen that question, we need to, so I guess that's a very hard and sort of vague question. And so a more specific question that we actually can answer is trying to understand what the root cause of instability is for systems like those found by Kepler. And to sharpen that question further, there's a key piece of evidence coming from the observation, and that is the period ratio distribution. So what I'm showing here, this is the period ratio of planets in multi-transiting systems found by Kepler, and this is just the number, this is the frequency of those pairs. For reference, Earth and Venus and basically the terrestrial planets in the solar system have period ratios sort of in this range. The gas giants are out here. And some of these multi-planet systems are dynamically compact, including Kepler-36, which I mentioned earlier, with these very, very compact orbits. So more compact orbits are going to be less stable for the same mass and eccentricities. And so it is this region that we want to understand to really try and understand instability for these systems. So the actual research question that I tried to answer then is how compact you can have two planetary orbits be while remaining stable.
Are there any observed with a ratio of exactly 1?
No, I don't think so.
And there's no Trojans or anything like that?
There's no Trojan planets. There's, I guess, some evidence that there might be.
The Trojan follows Jupiter at 1 radian, or at 60 degrees.
Yeah, 60 degrees ahead or below Jupiter, but with the same orbital period. And actually, I'll come back to that in a second. But so I think people have done stuff by stacking light curves and phasing the orbits properly to show that there might be some slight decrease in light at those spots. So there might be small bodies that are Trojans, but there's no Trojan planet. Yeah. So I personally, I get very excited about this question when I look at a picture like this, which shows as a function of initial conditions, so period ratio between planets and the initial angle between the planets, the location in black, this is where unstable orbits are in phase space. And in white are regions where I integrated, and I found that the orbits were long-lived. Now what you can see is that there's a lot of structure in this plot. And so that tells us that although orbital instability is this complex process, it's something that we should be able to understand. And in particular, we should be able to understand it by looking at resonances, because you'll notice that these features are associated with mean motion resonances, where the orbital periods are a rational number. So again, as I mentioned before, when you have this resonant configuration, you can have the longitude conjunctions where the planets meet, always occurring in the same phase of the orbits. More generally, you can have it oscillate about a fixed point in the orbit. So here I'm just showing you where conjunctions happen. And then there's this case where you're not in resonance, and the longitude circulates about the orbit. So these three phases of motion of being at a fixed point, oscillating about a fixed point, or circulating about a fixed point are very analogous to the motion of a simple pendulum. where you can have, I'll just point out, this is the phase portrait of the pendulum, so this is the momentum of the pendulum and its angle. And these lines are lines of constant energy. So just like the pendulum, conjunctions can always happen at the same place in the orbit. They can oscillate about it. Mm-hmm.
So this is the pendulum, or this is the...
So this is the simple pendulum, and
the other...
it's analogous, and I'll show you the Hamiltonian in a little bit, and you can see. But yes, you can have oscillations about a fixed point in the orbit, or you can circulate about a fixed point in the orbit. And that corresponds to the pendulum circulating about its point of support. And so what's important is, in both cases, this resonance area, it's not like you need a very specific configuration to be exactly at resonance. There's a wide range of initial conditions that correspond to being in resonance. And so this resonance has some non-zero width. So we use resonances to study stability then by applying something called the resonance overlap criterion. This is due to Chirikov. And it states that if you have a region of phase space that is simultaneously in resonance for more than one resonance, then that overlapped region of phase space is going to be chaotic. And we can use this as an effective criterion for instability because chaotic orbits often show instability on short timescales. So a criterion for chaos can be used as a criterion for instability. We're applying the overlap criterion to a system of 2 planets. This is building off of previous work, which applied the criterion to a star and a planet on a fixed circular orbit, and it was studying the motion of a test particle in this potential. So an example would be like our sun and Jupiter and an asteroid, and then these white curves are in the rotating frame, the lines of the effective potential. So these are contours of effective potential. And L4 and L5, these are where the Trojans lie. These are stable fixed points. So asteroids that start here will stay here stably 60 degrees ahead or behind of Jupiter. This picture, this circular restricted 3-body problem, where you only have 2 massive objects and they're on a circular orbit, is adequate for our solar system because our solar system has one dominant mass planet, which is Jupiter, on a nearly circular orbit. However, there's no reason why it should work for exoplanet systems like the Kepler systems, because those have comparable mass planets. They can both be eccentric, and so we need to actually study that more complicated system. And it is more complicated because there's more degrees of freedom, because you have 2 massive bodies now, and they both have eccentricities. So you guys asked a lot of questions, so I'm running short on time. So I'd like to just state sort of quickly what we do and then show you the results. So I'm going to have to skip over some slides, but which is fine. But just very briefly, what we do is we need to identify which are the most important resonances, and then figure out their widths, figure out when they overlap. So for the systems we're interested in with these small period ratios, so the compact systems, the most important resonances are going to be first-order resonances. So here, we're talking about mean motion resonances where the period ratio takes this form, where m and n are integers. So this line here just represents the possible period ratios of the 2 planets. A first-order resonance, when n equals 1, corresponds to, something like the 3:2 or the 2:1 period ratio. When n equals 2, you have second-order resonances, and that's something like a 5:3 period ratio. There's also third-order resonances and fourth-order resonances, and so on. So in principle, there's this countably infinite number of resonances that we would need to take into account. But luckily, the strength of the resonance, so how wide it is in phase space, actually depends on the eccentricity to the nth power, where n is the order of the resonance. And so for nearly circular orbits, the most important resonances are the first-order resonances. And those all lie in the range of period ratios between 1 and 2, so these compact systems like Kepler found.
So that Faraday is the mathematician,
Yeah.
one of the
Yeah.
Faraday-Taylor modular forms?
So I know that this is called the Faraday sequence, and it's after a mathematician, but I'm not sure what else he's done. Yeah. Okay, so I'm going to have to skip slides. I'm sorry. I can say that this is the actual Hamiltonian that we work with. So it's related to the Hamiltonian for two massive planets and a star interacting gravitationally just through a sequence of canonical transformations. And you can see that it does look something like the pendulum. So there's a momentum squared term, and then there's this angular dependence. And the difference is just that the coefficient in front of the pendulum depends on the momentum, whereas for the pendulum it doesn't. And so the phase portrait for resonances looks like the pendulum. It's just that now the momentum depends on the period ratio and the eccentricities, and this angle is telling you where conjunctions happen in the orbit. So this is what the boundary of the resonance looks like for the 5 to 4 resonance. What you can see is that it looks like 4 copies of the pendulum.
Sorry, but in your Hamiltonian, you have less variables than in the complete.
Yeah, so
one.
that's the, yes.
And why is it not time dependent still? I mean, don't you expect?
So in this problem, there's no time dependence, and it turns out that when you're near a resonance, that there's canonical transformations that show you that you're basically reducing the number of degrees of freedom, and you're not adding time dependence because there's conserved quantities, and that's what allows you to reduce. Yeah. Okay, so I think that I'm going to have to skip all this, but I'll just say that we apply the resonance overlap criterion to systems of 2 planets, and so we derive their widths and we figure out when they overlap. And the criterion that we come up with is that instability occurs if the initial separation between the 2 planets is less than this critical value, where epsilon p depends on the total mass of the planets to the 2/7 power. So this is a stability criterion now for pairs of compact planets. Okay. So to conclude, and I'm sorry I had to skip the details, but the question that we wanted to address was how compact you can make 2 planet orbits be while remaining long-lived. And the answer that we came up with is that you couldn't squeeze 2 planets closer than this criterion. And this was the result for initially circular orbits, and for the eccentric case, I refer you to our paper.
What's that star?
Yeah, so that's the mass of the star. Yeah, and then M1 and M2 are the masses of the 2 planets, yeah. So what I didn't get to totally explain, but I hinted at, is that there was this structure of unstable phase space that I showed you before, where the black points represent unstable orbits and the white points represent stable orbits. And that there was this structure because something having to do with resonances. And the reason for that is because these black areas are actually where, say, this is the 6 to 7 resonance. It's overlapping with the 8 to 7 resonance here, and that's why there's this chaos in between them. Yeah.
And there is fractal structure of this white spot.
Yeah. So actually, what I'm not saying is that in between each of these ones, there's more resonances.
Yeah, I can see those there.
Yeah. And these are actually the second order resonances that I briefly mentioned.
Is fractal structure related to the 2/7 power?
No, because in that calculation, we only took into account the first order resonances. So what I want to convey, though, is that resonance overlap is what helps you understand this picture, and so this is the right framework to work in for studying stability of planetary systems. And it's actually pretty straightforward to extend these resonance overlap criterion calculations to systems with more planets and more interesting orbits, although you need to take into account more resonances.
So Kepler 36, your favorite, was in a 7 to 8, right?
Or it's close to 7 to 6, yeah.
Or 7 to 6. So does that mean it's escaping this criterion because it's in one of these little holes?
So,
or is it actually meeting its...
So I will just go back to here. So what this plot is showing is basically the color scale here. This is on the same panel of period ratio and initial angle between planets. The color scale denotes the instability time. So the time scale for instability gets shorter if there's less overlap. Underneath every single one of these colored points is a black triangle, which denotes that the orbit's chaotic. And what you can see is that there's sort of this fringe up here, where things are chaotic but they're long-lived. And so these aren't the right parameters for Kepler 36, but Kepler 36 would essentially live up here.
Wait, now that we know more, can you tell us why Kepler 36 is your favorite system?
Yeah, so Kepler 36 is chaotic. It has an incredibly short Lyapunov time, which is this time scale for exponential divergence. Yeah, the time scale...
What is it? What is the Lyapunov time?
Like 10 years.
Wow.
Yeah, but it's still long-lived, which is the really fascinating thing.
And what is it for our solar system? Hopefully 1 billion
years? It's many. Well, the solar system is also interesting because the Lyapunov time is something like 10 million years, and that's still short compared to the lifetime, but it's very long compared to the orbital periods of the planets, whereas for this system, the Lyapunov time is only like 1,000 times the orbital period of the planets. Yeah, so
Interesting.
Kepler 36 has very interesting dynamics, which is why I
And
like
how
it.
far away is it?
Oh man, I think, I'm not sure actually. I think most of the Kepler systems are, I think I would say on the order of hundreds of light years away, but you might know better than me. Yeah. So.
Yeah, you're not gonna visit anytime soon.
Yeah.
I'm just worried about flinging something in another direction.
So that's actually my next question. So I mean, there were these kind of microlensing claims that they found so many free-floating planets, and that must be due to all these interactions.
Yes.
So what's the reason? I mean, at least there was a press release, so of course we have to be very careful with these things. But what is, and then of course, next generation W-first and so forth actually will include a microlensing component for exoplanets. So what is your view on that?
Well, okay, so I guess I would say that the microlensing results so far have been, all they can say is that the separation between the planet and the star is large. So that might be free floating, or it might be something like 100 AU or something. So they're widely separated or free floating planets. I guess the rate, so they claim that there's something like 2 Jupiter masses of free-floating planet per star, and those rates are too high, I think, to explain what planet-planet scattering is sort of the consensus. But the error bars on that number is incredibly big, so it's like 2 plus or minus 2 or something. Mm-hmm. So I think that we'll get a better, there's something interesting there, but I think we'll answer it better when there's data from W first. Yeah. Okay. I'm also, well, I guess I'll just say that the question that I started out with was that we want to understand whether or not instability affected the Kepler systems or not. And the first question that we answered was just trying to understand theoretically what causes instability of these systems. But the next step is to actually look and to see if there's any evidence that instability occurred. And so you might imagine that instability would take a flat planetary system like this and turn it into a more dynamically excited system like this. And if we looked here, we would likely only see one planet transit. Whereas if we looked at this system, we'd see multiple planet transits. And so there has been evidence that the single transiting systems found in Kepler do share some qualitatively different observational properties compared to the multi-transiting systems. So there's some evidence that this is a dynamically different group. But more work needs to be done to actually show that instability can produce this population or not, or match these observed differences or not. And so in the future, I'd like to work on that using numerical simulations, and then there's missions coming forward, like TESS, which is a transiting mission, and also K2 and Plato are both transiting missions, and data from that will help us better address this question as well. Okay, so to summarize then, what I hope I've convinced you is that exoplanets are common and that they're extremely diverse. And furthermore, we're at this point, this very interesting point, where the systems that we found, we're not really sure if the solar system fits in entirely with them. And in particular, while the solar system certainly might fit in with these, it has a giant planet at a large orbital distance. Most planetary systems that we know of are these small planets orbiting close to their host star. And it looks like the solar system might be different from them because it doesn't have that. So the big question coming forward is trying to understand why. The first step to understanding these systems and how they formed and evolved, so planetary systems as a whole, is to first characterize them. And I described the work that I've done trying to characterize these systems, or trying to understand how this characterization proceeds using transit time variations, which is due to orbital dynamics between planets on short timescales. And that's going to help us better understand these Kepler systems. In the second part of my talk, I described work that I've done trying to understand the dynamics of systems on longer timescales. And in particular, trying to understand this process of orbital instability, which, after planets form in a disk, is one of the processes that affects planetary systems, which then perhaps leads to this diverse population that we're seeing today. So I'll end there. Thank you.
More questions? Imagine that some of the strangeness of our system is observational bias.
Yeah, so that's kind of the thing that it's an excellent point. We can say it might be odd that we don't have a planet like this, but if we could have observed longer with Kepler, we might have found that planets out here are also very common. And so we're not really sure yet if we're uncommon or a bit strange, or if it's just because we haven't observed long enough. But it is strange that, or it might be strange that these small planets close in are so common and we know we don't have those.
I've taken the position in the literature that we are in fact strange. So
Yeah.
when we try to account for these selection biases, we do find that super Earth, things that are 2 or 3 times the radius of the Earth, are much more common in the Earth, even at 1 year period. But, you know, as Kat said, the jury's still out.
Yeah. Another way of looking at it is that the solar system has a giant planet at a large or at an intermediate orbital distance, and we know that only 10% of stars, or we think that on the order of 10% of stars have that. So in that sense, too, the solar system is not like most systems. Yeah.
Do you find, obviously it's a very strong prediction that exoplanet systems should be stable, at least on fairly long timescales, because they should be rare. Do you find any examples, are there any hope of systems that look like they might disrupt
as we're
in
watching?
or in the near future, or things that just look like they have short timescales, like should disrupt in 100,000 years or 1,000,000 years? Like even 1,000,000 years would be a very surprising kind of system.
Yeah, I think that we'd have to observe a lot more systems, I think, to be able, just statistically, to catch one that was.
So for instance, does everything so far meet your stability criterion? Everything known?
So for some of them, we don't know the masses.
Yeah, but when you do.
Yeah, I think presumably everything's going to meet it. I guess if there is the chance that they might fail it, but then if they do, what we can say is that they're in a resonance.
Right,
yeah.
It would be a strong
So that would be
prediction.
pretty cool.
So it would be very exciting.
Yeah.
I have one related question, which is the implication of your talk is that systems start cold with circular orbits and a flat plane, and dynamics always makes them hotter in the sense of more eccentricity, more inclination. Is that generic? Because if that would be nice if there was a generic prediction like that, because that would allow us to make much more blunt tools for looking at this. Right now the tools are very precise. They involve MCMC running the whatever on the side of the loop, running n-body simulations inside the loop, which is brutal.
Yeah.
If we had blunter tools, so are there really generic things you could say, or?
I think that for giant planets at these large orbital distances, pretty generically, planet-planet scattering is going to lead to ejection or high eccentricities, and that's because the Keplerian velocities at large orbital distances are small compared to the biggest kicks the planets can give each other. But for the Kepler planets that are very close in, their Keplerian velocities are very large because they're more tightly bound. And so for those systems, it's less clear what the outcome of instability is, that if there's instability, it'd be more likely to lead to collisions instead of any ejections. And collisions actually damp eccentricities and damp inclinations.
Because they remove high eccentricity systems from
the... partially because of that, and then, that's basically,
There are also tides.
There's also tides too.
Right, which recircularize things.
So I think for planets at large orbital distances, it's generically true that systems will get hotter with time, but for the ones close in, it's harder to say.
So what about systems, I think it's called the Longterm effect, where they see that actually some of the planets are moving the other direction. So one are moving this way and the other's moving this way.
Okay.
So that's the only reason you can get that is they mentioned from scattering.
Oh.
But then so that would be kind of a different kind of outcome where it's not necessarily, I mean, I don't remember the details in terms of yes, it makes it hard, but it's something that doesn't disrupt it in that sense. But it still has a very important kind of observational outcome.
Yeah, so one of the differences between the multi-transiting systems and the single-transiting systems in Kepler that's been suggested is that the single-transiting systems have higher obliquities. So this angle between the star's spin and the planet's plane, which is extremized when the planet's going the opposite way as the star is spinning, that angle is higher for single-transiting systems. So that is a sign that maybe there's been some dynamical effects. Yeah.
Any other questions?
I suppose that someone has to ask about that Dyson sphere thing.
Why didn't you address that?
Exactly.
The community's all going to pull out their notes now.
I guess I would say that just because we don't have an explanation for something in terms of things that we know happen, so things like an asteroid population or small bodies or a planet being disrupted by tides and making small bodies, doesn't mean, just because we don't have a satisfying explanation for that doesn't mean we should invoke something extreme.
But we don't have an explanation. I mean, we don't have a dynamical model.
Can you explain for the not?
Yes. So the idea is that there is this a Kepler star that shows basically decreases in its flux that are large and they're aperiodic and they're all short times. So timescales that I don't know if it's sub-day or days, but it's short timescales. And so you can't explain that with just a single transit because sometimes up to maybe half of the light from the star is blocked. So it's clearly something large or extended that's blocking the light. And because it's aperiodic and it's sort of, so it's not a transit basically of a planet. And so probably the simplest explanation is that it's small bodies that are spread out into a disk. And so if there's enough, or maybe it's an extended from small bodies that are being sort of blown apart by starlight or sort of because of stellar winds or something, that there's sort of an extended cloud of material and that's blocking light. So that's probably the simplest explanation, but I guess there's some difficulties in actually getting the theory to match with the observations in terms of the depth of the dips and also the timescales and the persistence of them. And so there was a group that said maybe that these dips are caused by alien megastructures.
So make the press
yes,
go crazy.
Okay, so to ask the other obligatory question, what's the relationship of this kind of dynamics to gravitational radiation and gravitational, because it's possible that the world will look very different in 5 or 10 years in terms of observations of dynamics.
Yeah, and so I think that I would say that, it's all I'd say both cases involve Hamiltonian dynamics of gravitationally interacting bodies with some slow dissipation. So there's examples of that in both cases. So for systems of planets, the slow dissipation might be caused by tides, or it might be caused by interaction with the disk, which leads to this slow migration of planets. But it's still basically adiabatic evolution of a Hamiltonian system. And for gravitational waves, the adiabatic, or the dissipation, is basically what's causing the inspiral. It's a gravitational wave emission. So I think that the same tools can be pretty directly applied to both, even though the actual configurations are very different. I didn't get a chance to talk about it today, but I talked about it last time for those of you who are here, that when planets interact with the disk, if you have two planets interacting with the disk, there can be convergent migration because the planets lose angular momentum to the disk, and so their semi-major axes change. And that means that their period ratios change, and so the planets can cross mean motion resonances, and sometimes they can be trapped in mean motion resonances. And so the analogous situation for an inspiral towards a supermassive black hole would be that, or for a binary, is that as their semi-major axis is changing because of the gravitational wave emission, they cross resonances between the orbital period and the precession frequencies. So it's possible that you could get trapped in your resonances that way as well, and that would show up in the gravitational wave signal.
Thanks a lot.
Cool. Thank you.